This question is about the electric fields and the magnetic field. So in this diagram, you see that these are the two plates having opposite charge and they have a uniform electric field. By the way, how do you know that this is a uniform field? Because we see that these field lines are parallel between the plates, right? And the electric field strength that we represent with letter E is same irrespective of the position between the plates. It is equal in between these plates. Rather, you are taking you are finding electric field strength at this point or close to the negative plate, electric field strength will be equal. And the potential difference between the plates is 120 volt. Okay, this is the potential difference, and this is the distance between the plates. So, what is the electric field strength between the plates? This is our first question, and I had explained you the concept of electric uniform electric field. So, electric field strength can be determined E is equals to V over D, right? It's equals to, actually, it is the potential gradient. Remember that it is also the gradient of potential distance graph, right? Okay. So we know the potential difference, and here the V represents the potential difference. So E is equals to 120 volt divided by the distance between them is 0.08 meter, right? And that is, so its answer is 1500 Newton per coulomb. And not only this, you can also represent it 1500 volt per meter. So students, this 1500 Newton per coulomb practically means that, let's say if this charge is 1 coulomb, right? So then this positive plate and due to this electric field, a 1500 Newton of force will be applied on this charge due to this electric field in terms of the scientific notation. So that will be equals to 1.5 times 10 power 3 volt per meter. Okay. So this is what our mark scheme says. Okay. Now the next question. Show that the acceleration of the alpha particle is 7 times 10 power 10. Okay. Now when you will release the alpha particle in this, as we see here, this is the alpha particle. So what is the alpha particle? So dear students, you know that alpha particle is also called helium nuclei, which have the two protons and the two neutrons, right? So it have a charge Q is equals to positive 2e. All right. So if you are releasing this charge from this point, clear, that have 2e, okay, alpha particle. So any positive charge always experience force in a direction of electric field. Okay. So that's why this is a concept of drawing electric field lines, because electric field lines show the direction of force exerted on a positive charge. Okay. Uh, so this is exactly the direction of the force, which is in the direction of electric field, and this force is equals to electric force, which is E times Q. Okay. So if you want to find out the acceleration, because this is the resultant force, right? So according to Newton's second law, this force will produce the acceleration, right? So this is equals to ma, right? Whereas this m is a mass of alpha particle. So we can say that alpha is equals to eq over mass of alpha particle. Okay. So now we can put the values 1500 times 2 times the charge of alpha particle, which is 2 times e, so 1.6 times 10 to the power negative 19 divided by the mass of alpha particle, which is 4 times the mass of proton, right? Which is 1.67 times 10 to the power negative 27 kilograms. So this will give us the acceleration with which it will be accelerated towards this negative plate. As a result, it will gain kinetic energy because it is attracted. Okay. So let me calculate value. 1.2 times 10 raised to the power 10 meter per second square. So as you see that this is a very large acceleration because force was very large for such a small size of particle, a small size particle, that is alpha. Okay, so that's why it will accelerate with this value. And okay, so the next question is calculate the time taken for the alpha particle to reach the negative plate. Okay, now one thing you should understand that this is a constant force, right? Why it is constant force? Because this is coming from a constant electric field strength. Okay, we had seen that electric field strength is constant, uniform between these two oppositely charged parallel plates. So when the electric force is not changing, so it will create a constant acceleration, right? So we can say it is an example of a uniformly accelerated motion. So which allows us to apply the Seward equation, right? You know that we always apply the Seward equations to find out these physical quantities. So if I just quickly show you that if this is an alpha particle, is at the time t is equal to 0 when it was just released, because it is accelerating, so you know that its distance will increase non-uniformly. Okay, because that is a property of a constantly accelerated motion. So but what distance that it has covered, that is 8 centimeter, right? And the displacement covered is negative 8 centimeter. All right, so if you want to find out the time, so what equation should we apply? We know that its initial velocity is 0, and we know that the s is equals to negative 0.08 meter. All right, and you know the acceleration also. So which equation should we apply? I think it's obvious that s is equals to ut plus half a t square, right? So let us apply this equation, right? And that is negative 0.08. This term will become 0, is equals to 1 over 2 into, because I'm taking the displacement negative because it's going downward, so that's why I'm taking, just due to the direction of acceleration, it is also negative here, right? Okay, because the time cannot be negative, right? So ultimately this negative sign will cancel out with this negative sign, and you can multiply 2 on both sides, and then you can move this thing, I mean, or divide this thing on both sides of equation to find the time. Okay, so I mean to say now it will look like this. Okay, and then you can take its square root because we want to find the time. So finally, dear students, the time value should be 1.49 times 10 to the power negative 6 seconds. So just 1.49 microseconds is taken by this alpha particle to cover such a small distance with such a huge amount of acceleration, right? So I think this makes sense to us. This is the time that it takes, and you can also apply, by the way, the second equation of motion, because any equation will work since it's moving with a constant acceleration. So v square is equals to u square plus 2as, right? So since it's moving started from the rest, so the v will be equals to the square root of 2as, right? So you can plug the values and we'll get the same answer. Okay. Now our next question is state in EV. EV is a electron volt, is a unit of energy, smallest amount of unit of energy. The kinetic energy of alpha particle when it arrives at the negative plate. Okay. So remember that the law of conservation of energy will not be violated even in this, at this microscopic level. Okay. From macroscopic level, from a universal level to this subatomic particle level, law of conservation of energy is always followed. So we can apply either the law of conservation of energy, or you can also apply the kinematics equation, right? So let me start with the kinematics equation. Okay, so this is a alpha particle that started from the rest, and imagine when it reaches at this point, it have a maximum velocity v that we want to find out. Okay, because you want to find out the kinetic energy, and the kinetic energy is 1 over 2 mv square, right? So to find out the kinetic energy we need the velocity, right? And we can apply the Seward equation. V is equals to u plus at, right? And this is 0, right? And V is equals to 80. Since we have a time, so we can apply this as well. So we got 107,280 meter per second. Got it. Okay. So our next step is to plug the value in this at this point. Okay. And for this, it's just substituting the values. So here the mass of the alpha particle is 4 times 1.67 times 10 to the power negative 27. So students, the energy that we got in joules is 3.84 times 10 to the power negative 17 joules. Okay. But since they ask us to convert it into the EV, right? So we must divide at this point this answer 1.6 times 10 to the power negative 19, and then this joule will convert into EV. Okay. So finally, we got the energy 240 EV, electron volts. Okay. So so this is the energy of the alpha particle, right? Now the second method, dear students, don't miss this method also, right? The method number 2 is actually about the law of conservation of energy, right? That is applicable for only the HL students. This is not included in the SL syllabus, right? So for example, so students, if you see the diagram from where the alpha particle is released, it is released just before, just from this point, very close to the plate. Okay, which means that the positive charge, having this positive charge carrying alpha particle, this positive charge carrying alpha particle plus 2e is so close to the positive plate that at this point, don't you think that it has gained the maximum electric potential energy, right? Okay, means that we have done an external work to stick it, to hold it close to the positive plate, because it cannot stay by itself, right? So we are providing the maximum work done, we are doing maximum work done to hold it, which is appearing in a form of increase in its electric potential energy. Now the work done is equals to the potential difference into the charge, right? Because this is, dear students, this is a gain of electric potential energy, right? And this potential energy will ultimately convert into, when it is moving to this point, at this point, dear students, it will have the maximum kinetic energy, okay, which is 1 over 2 mv square. Okay, so you want to find out the velocity, while this we can equate these two expressions, right? Delta v into charge, right, which is electric potential energy. Okay, that is equals to 1 over 2 mv square, right? You can say the loss in electric potential energy is equals to the gain in kinetic energy. This is the transformation of equation from one form to another, right? So this is the kinetic energy that we want to calculate. Okay, so don't you think if we put the values of the potential difference, that was 120 volt, and the charge is 2 times 1.6 times 10 to the power negative 19, right? So its answer will be in joules, right? You see. Okay, but if you want to convert it into EV, right, why not we divide it? Okay, because you know that we will divide it. So this value we will divide with 1.6 times 10 to the power negative 19. Now its answer will be in EV. So we see that this is cancelled out, and finally the kinetic energy is equals to 240 ev, the same answer that we already got from the other method. Okay, so this is a kinetic energy of alpha particle. Now let's go to the next. Now the magnetic field questions are starting. Now in this question they say that we have applied the magnetic field into the plane, right, into the plane. All right, and we are throwing a charge, and alpha particle enters the region between the plates with a horizontal speed of this. Okay, okay, this is very interesting line. The particle is not deflected. Interesting. Okay, why the particle is not deflected? Okay, let's imagine if there's a no any magnetic field applied into this region. Where is the what is the possible trajectory of this alpha particle? This has a charge plus 2e, right? This alpha particle could go in what direction? Dear students, you can predict, right? It can make this parabolic path. It can go depending on its speed, right? But it will go towards the negative plate, and it can even escape this plates, okay? But it will deflect downward, okay? So it means that due to this electric field, if this is an alpha particle, 2e charge, so we see that this is a force that is exerted on it. That is an electric force EQ, right? But why it is going undeflected? There is only one reason, that an equal amount of magnetic force is applied on it, that is upward, which is, that there's students QVB sine theta. And I explain you why. So students, this is the alpha particle, right? And what is the direction of this alpha particle? Initially, it is thrown in the direction of x-axis, positive x-axis, horizontally, right? With some velocity v, okay? And that velocity is given over here. Okay, and what is the direction of the magnetic field? You see that the magnetic field is applied into the plane, right? So this is the direction of the magnetic field. And what is the angle between them? 90 degrees. It means that whenever a charge is thrown in a magnetic field at 90 degrees perpendicular from whatever the direction it is thrown at, it experiences the maximum magnetic force, right? So that's why we will put here sine 90, okay? And it will become QVB, okay? Because that is a maximum magnetic force. And what is the direction of this magnetic force? We can apply this rule, right? So this shows velocity of the charge. This is the magnetic field into the plane, and that is the force. So we have thrown it horizontally to the rightward. Magnetic field is applied into the plane, so this is going into the plane, and this finger is showing the direction of force applied, which is vertically upward. That's why I have shown you, dear students, the force is in this direction, okay? So this is a reason, okay? So let us solve it. So QVB is equals to EQ, right? And you see that the Q and Q is cancelled out, so VB is equals to E, right? And what is the magnitude of the magnetic field? That's what we want to find out. So B is equals to E over V, right? And let's put the values, right? This is the same electric field. So if it is same, then it is 1500 Newton per coulomb or volt per meter divided by 5 times 10 raised to power 5. Okay, and the unit is Tesla, right? So it should be 300 times 10 to the power negative 5 Tesla. Okay, and that you can write 3 times 10 to the power negative 2 Tesla. Okay, so this is a magnetic field strength. Okay, for this magnetic field strength, the charge will go undeflected. Okay, and not only the alpha particle, all of the charge, because you see that this equation tells us that it does not depend on the charge. Whatever charge particle you throw in, positron or proton or electron, right, or beta particle, right, that all will go undeflected if you produce or if you sustain these circumstances for electric field and magnetic field. Okay, so yes, this is the 10 to the power negative 3 Tesla. Okay, now the last question. The alpha particle in C is replaced by an electron, right? So what will happen? The electron enters the region with the same velocity, okay, and draw on a diagram the path of the electron. Okay, so we had already discussed that when the magnetic force is equals to the electric force, so you see that the VB is equals to E. So V is equals to E over B. So this V just depends on the electric field strength and magnetic field strength, right? So if you have thrown this alpha particle electron perpendicular to electric field and magnetic field, so it will go undeflected, right? Okay, so there will be no change in its velocity, right? So particle will move undeflected, right? Okay, or you can also say or horizontally.